Hey, uh, looks like I'm recording. Maybe not. Okay, good deal. Guys, this video 38. This is the final video. It's the video we've all been waiting on, right? Uh, it's strange to think that we've got 38 videos or 37 behind us instead of 38. And I know you guys will be happy that this is the last one. Of course, I don't think anybody's going to be as happy as my daughter, so she gets her iPad back. But I don't know. It's been fun. It's been a learning experience. I have to say I have a lot better feeling about delivering an online class as I start video 38 than I did when I started video number 1. So still a fan of the classroom, but hey, this hasn't been bad at all. What I want to do in video 38 is I want to get into logistic regression more, and there's just going to be 2 parts. I'm going to get into a little bit about the theory, and I know I kept you over, so to speak, in the previous video, so I'm going to try to make this one a little quicker. And then I want to get into a situation where we have multiple predictors for logistic regression. And not going to get into any calculation of the beta estimates using matrix operations. We're just going to, use a data set, put it into R, and go from there. So, guys, a little bit about the theory. Again, kind of wanting to blend the theory with the application. Remember in the logistic regression problems, our response variable is binary. And take on values of 0 and 1. The probabilities can be thought of. Pi for 0 and 1 minus pi for 1. And clearly we could set it up the other way if we prefer to do that. Guys, this logistic regression follows the Bernoulli distribution. So we have a Bernoulli random variable where our expected value for y is given, and I'm running out of space here, is given as pi. I'll tell you what, let me go up here and do this. Given that y sub I is equal to the expected value, y sub I plus, of course, the error term. Now, unlike standard regression, our errors depends on the Bernoulli distribution. Not a normal distribution. So we can say y sub I, let me be consistent here with this. random variables. And the expected value for y sub I is just pi sub I. Where all right. Now, the calculation of the estimates so B0 is an estimate of beta 0, and B1, of course, is an estimate of beta 1. Requires us to look at the likelihood function and ultimately look at the maximum likelihood function. So, guys, we'll start out by saying that the probability and I want to bounce this back off of the Titanic example. So the probability that a male survived would be y sub I, and the probability that a male didn't survive would be 1 minus pi sub I. So changing it up a little bit. Before I said, we have binary of zeros and ones, and I think I let 0 be pi and 1 be 1 minus pi. Depending on the way that we set up the problem, we can establish it either way. So guys, we can clearly represent a family of functions here. Hopefully you remember the Bernoulli distribution. There's a reason I focused on it so much early on, and there's a reason it was on your first exam, is because I knew it was going to be coming up later on. So guys, y sub i's are either going to be 0 or 1, and of course we're going to have n observations. Okay? Now we can look at the joint probability distribution. So we can think of I'm going to go through this pretty quickly because, guys, we've already done this. Can be the product from I equal 1 to n of each of these which, of course, in our case, let me write really big here. Following the Bernoulli distribution. Okay? Well, boys and girls, what would we do next? We would take the log, because it's going to be easier to differentiate. So log, again, guys, think natural log. So we'll take the log of, well, I did call it G, didn't I? Yeah. Which of course gives us the natural log I equal 1 to n. It's kind of weird having pi as your operation and then as your probability. Wish I'd actually used p instead of pi now. I wasn't thinking ahead very well, was I? So guys, this is going to be the sum from I equal 1 to n of, let's see, we're going to have y sub I, natural log, I sub I. So we're multiplying, so this would be plus 1 minus y sub I times the natural log of 1 minus pi sub I. Okay, should look extremely familiar. So let's clear this up a little bit. So we're going to have, I'm not going to put the subscript, so we're going to have, let's see. So we're going to have the sum of y sub i's natural log of y sub I minus pi sub I. We're going to look at the natural log of the odds plus, shoot. Alright, let's see what's going on here. I get the natural log of 1 minus, so we got, okay. So this is actually going to be the sum of the natural log, 1 minus pi sub I. Okay, I did some mental stuff there. So we got natural log 1 minus pi, natural log 1 over, oh, okay, yeah. 1 over pi minus, yeah. I'll tell you what, I don't know if this is clear or not, how I go from the step previously to here. And I hope I did it correctly, and I know I did. But that'll actually be a homework assignment that, to make the connection between the previous step and this step, and it's not high-level stuff. All right, gang, we can show that this part right here is going to be the same as 1 plus e beta 0 plus beta 1 xi inverse. And we can show that this part right here is obviously just beta 0 plus beta 1 xi, as we've shown before. Still kind of, let me think this one through. Yeah, good. Okay. So therefore, we can express the log of the likelihood function with respect, and it's going to be the sum 1 to n, y sub i's 0 plus beta 1 x sub i's, and minus, let's see, got, so if we take 1 over the quantity 1 plus, we're dividing, so we have to make that a negative, yeah. So minus the sum I equal 1 to n, the natural log of 1 plus. So you guys insert that into the parentheses. Which gets us exactly what we want. We have, in terms of our data, in terms of beta 0, beta 1. Now, guys, remember there's no closed form. So we depend on the iteration process. I'm going to teach you the iteration process that I was taught, called the Newton-Raphel, I forget how to say it actually, along with the maximum likelihood estimation. But for now, we're going to depend on the computer and depend on R to take care of this for us. Okay, so once beta 0 and beta 1, which again are estimates of, once B0 and B1, which are estimates of beta 0 and beta 1 are found, then we have that the predicted probability can be found by taking by this yes, by that. All right, guys, it's going to be the end of the theory for logistic regression for this class. We're going to get into this a lot more in the next one. Fun, right? All right, guys, let's work a problem. Now, let me show you what I've got, going on here. I got this data set that I found some time ago, and it's pretty cool. It got into whether or not, well, if it opens up. Very slow. It's whether or not sexual harassment will be reported. So obviously we have a logistic regression situation here because it's either reported or it's not. And not reported is 0 and reported is 1. The variables that we're going to use to predict this are the age of the victim, the marital status. 0 is not married, 1 is married. This is called a feministic scale. Apparently they were given some sort of test that measures who knows? I don't know much about that, but apparently a higher score means more feminist beliefs. Frequency, that would be how many times the act was how many times it occurred. And there's a severity. And the higher the severity, I think this is from 0 to 10, the victim actually recorded how severe they thought it was. So that'd be obviously something that you would want to control for in your model. So guys, I'm going to shut this down. And I've got it saved on my desktop. Right here is just SEXHAR. So what I want to do is get into R and make it happen, okay? So first of all, as we should all know by now, set our working directory. Let's go get our data. Let's attach our data so we can do something with it. And let's take a look at our data. So we've got a pretty good data set here, 343 observations, and again we have the variables. Now, to keep from going up every single time, what I like to do here is get the names of the data down, and let's just think this through. Now, hopefully by now you realize that what we have to do is we have to go back through and find the variables that are non-quantitative and set them as factors. Well, age is fine. Marital status quoted or coded 0 and 1. So I'm just going to call this marriage. So I need to set MSTAT as a factor. Feministic or whatever. You can tell I don't know much about that, right? The feministic scale is quantitative. The frequency, is quantitative because 0 is absence of occurrence, and let's see. So frequency would be quantitative. The severity, that's on a scale from 0 to 10, so that's cool. So guys, we clearly need to set report as a factor. All right, so gang, let's run our model, see what happens. So remember, we got to go GLM. So I want to predict report from age plus, guys, I got to use MARR plus frequency plus severity. And that is it. Remember, guys, if you run this, you're going to get R is going to think you're running a multiple linear regression. We don't want that, so we have to instruct the instruct R to run logistic regression by going family equal binomial. All right, gang, let's see what happens. Here's our coefficients, and without more information, what do we know? Well, I'll tell you what. Let's tap into this one right here, the severity. So let's come down here and do an interpretation of severity. So do hashtag. So we would say as the level of severity increases 1 unit, the predicted natural log of the odds of reporting the incident increases 0.49. Now again, what does that mean? To me again, taking the natural log of the odds is very, very, very hard to interpret. So what I'd want to do next is probably look at a summary of the model, and what this allows us to do is to get into the the p-values. So when I look down through here, the only predictor that was statistically significant was the severity. The least statistically significant was the frequency. and whether or not a person was married. Um, so, and down here we can see that the number of iterations using the Fisher scoring process for us to come to the optimal model was 4. Now, again, that's all fine and dandy, but it's still extremely hard to, wow, my Bailey's best friends are blowing up her, iPad. So anyway, that's hilarious. So guys, let's look at something that. Hold on, I need to look at my notes. I still don't have this. This coefficient. I always forget when doing the EXP. Actually, how to do that. And guess what? I think I've thrown that away. Lovely. All right, yeah, here I wrote it down. So, guys, it's going to be much better to look at to exponentiate the values. So, if I take E and raise it to, for example, let's just do the severity. So if I take E and raise it to the 0.48416, what I'm going to do is I'm going to take the natural log of the odds and convert it to odds. So well, let me do that. Why not? Well, I'll tell you what. Just do that on your calculator. Take E and raise it to the 0.48416, and I get 1.63. So the odds for severity are E raised to the 0.488416, which I get to be on my calculator is 1.63. Okay? So this tells us that the odds, well, tells us controlling for age, marital status, let's see, age, marital status, and frequency. As the severity level increases 1 unit, the odds of reporting the incident increases 1.63 times. So almost twice as likely controlling for the other variables in the model. It's almost, again, 1.63, but it's almost twice as likely for the person to report the incident as the severity goes up, and that should be no surprise at all. But guys, it'd be kind of a pain to go through and do to raise all of these to the estimates to the E power. So what we can do here is we can do EXP coefficients of our model, and then you can see that the severity down here is the 1.63. That I keep losing my mouse here. Wow. Here's the 1.63 that we got when doing this by hand. Now, important is we always want to look at our confidence interval, because this is, one sample of, for the most part, infinitely many. So what I would want to do here is look at the EXP confidence interval of our model, and we'll get the confidence intervals for each one. Now, if you notice, I think I actually told you this incorrectly a while ago. If our interval contains 1, that means that the event is equally likely. So we're not really worried about our intercept, but notice that age contains 1. This interval contains 1. They all contain 1 except for the last one, which is the one that's statistically significant. So, with a 0.95 probability, we could say that the odds of reporting the incident controlling for the other variables in the model increases from about 1.4 to about 2, with again each increase in severity level. Well, guys, I tell you what, I'm going to make this one a short video. It's going to be our last one. It's been fun. It's been real. We're going to talk more about this on Friday. Of course, by the time you watch this video, we will have already met. So, guys, that's I don't know how long I kept you on this one. 31 minutes. Hey, that's a good, a nice way to end things. So. Guys, this is the end of the final video, and it feels pretty good. Take care.